Good morning, everyone. It is my pleasure to attend the conference and deliver a presentation. My topic is Optical Fiber SPR Sensing Technology for Microfluidic Applications. My name is Zhang, and I am from the K-Lab of In-Fiber Integrated Optics, Ministry of Education of China, Harbin Engineering University. So, what is microfluidic? It is a technology that uses microchannel to process or manipulate microfluids. It is also known as microfluidic chip technology, lab-on-a-chip, or microanalysis system. It is widely used because of its advantages of miniaturization, integration, low cost, etc. Microfluidic optics is developed on the basis of microfluidic technology and combined with modern optics and optoelectronics to form a new cross-cutting frontier discipline and technology. The strong interaction between light and fluid can be promoted by integrating the optical system into the microfluidic chip. During this process, the characteristics of light, such as wavelength, amplitude, phase, polarization, intensity, and frequency, will change. The fluid detection can be realized by analyzing the changes of output light characteristics. It can be used for drug delivery and sorting and analysis of pathogen or metabolites. There are four methods commonly used in microfluidic optics. Fluorescence detection, which has high selectivity and can be used for cell counting. SERS, which is surface-enhanced Raman scattering, which can determine the molecular structure. Optical microcavity, which is used to enhance the interaction between evanescent field and microfluid for the detection of external environment. And surface plasmon resonance, which is also called SPR. The resonance peak caused by electron oscillations on metal surfaces can be used to analyze the extremely small refractive index changes. Among these detection technologies, SPR is a non-label detection technology which can avoid the use of fluorescence, radioactive labeling, and enzyme, and has the advantages of low cost, high sensitivity, integration, and reusability, and has bright prospect. So, what is SPR? When a beam of p-polarized light is totally reflected at the interface between the prism and the metal film, the evanescent wave in the metal film will cause free electrons in the metal to generate surface plasma wave. SPR occurs when the frequencies of the surface plasma wave and the evanescent wave are the same. At this time, the amplitude of SPW reaches the maximum. The incident light energy is absorbed by the metal surface electrons, and the reflected light energy drops sharply, which results in the form of a resonance dip. SPW is limited to tens of nanometers on the surface of the metal layer, but it can penetrate into hundreds of nanometers of dielectric materials. Therefore, SPW can detect very subtle changes of the dielectric constant near the metal surface. In addition, specific analysis of target molecules can be achieved by functionalizing metal surfaces. SPR configurations mainly include waveguide coupling structure and optical fiber coupling structure. The waveguide coupling structure has high sensitivity and robustness, but it has bulk system, which limits its miniaturization and integration. In contrast, the optical fiber coupling structure has the advantages of lightweight, compact, long transmission distance, and distributed sensing compatibility. In recent years, fiber optic SPR sensor has been widely concerned by scientific researchers and became a substitute for prism coupling system and has wide applications in the field of basic biochemistry to pathological detection. Fiber optic SPR microfluidic sensor is to combine microfluidic technology with optical fiber SPR sensing technology and achieve the detection of low-dose flood samples with high performance. Fiber optic SPR microfluidic sensors can be summarized into two types according to the positions of microfluidic and optical fiber. The first type is integrating conventional optical fiber SPR sensors into microfluidic chips. That is, various optical fiber SPR probes are packaged and embedded into optical microfluidic chips to detect flood samples in channels, and optical fibers are only used as the sensing elements. The second type of optical fiber SPR microfluidic sensor is directly filling the liquid sample into the optical fiber. This kind of optical fiber has a special structure. The liquid microchannel and fiber optic SPR sensor are integrated into one optical fiber. Therefore, it is convenient for preparing miniaturized, high-sensitive, and compact microfluidic optic devices. Although the optical fiber SPR sensors are widely used in the field of microfluidic optical detection, it has advantages in environmental monitoring and biochemical analysis. It also faces many challenges. All those challenges are concluded and listed here. We need the sensors with high sensitivity, large dynamic range, and compact structure which is easy for miniaturization and integration. First, as the medical diagnosis field tends to be more and more micro schemes, the target molecules usually exist at very low concentration. So, optical microfluidic devices are required to have higher sensitivity. Second, due to the diversity and complexity of chemical molecules and biological cells, a single optical microfluidic device cannot cope with the detection of multiple markers and cannot be reused, resulting in a waste of resources. Therefore, optical microfluidic devices are required to have a large dynamic working range to meet various detection requirements. Third, the integration of optical microfluidic devices is crucial for biochemical detection, DNA sequencing, and other fields. However, most optical detection functions for microfluidic applications require the use of external optical systems or the embedding of optical fibers. Although these devices are flexible, they do not have the potential for robustness, stability, and mass production, which limits the application of portable instruments. In order to achieve the targets we've mentioned above, we proposed 3 different optical fiber SPR sensors to realize high sensitivity, large dynamic range, and compact structure. The first SPR sensor is made based on all-fiber Bessel-like beam. This sensor is proposed to enhance the efficiency of SPR generation to achieve high sensitivity. A common way to generate fiber optic SPR is to transmit light into multimode fiber, grinding the probe and coating a layer of gold on it. But there are various modes in multimode fiber. Different modes have different reflection angles at the interface between the grinded fiber and mental film. Thus, the efficiency of SPR is low. The proposed sensor is to connect a section of multimode fiber to a single-mode fiber. LP01 mode will be converted into LP0N mode. The output light field of these modes are like concentric rings. They have almost the same reflection angles at the interface between the grinded fiber and metal film, Therefore, we can achieve smaller divergence angle and more efficient excitation. At the same time, the surface plasma mode has more overlap with the surrounding medium to be measured, which promotes improvement of sensor sensitivity. Because LP0M modes have different propagation constants, it means that different modes will propagate at different speeds inside the multimode fiber. Thus, the output light field distribution of the multimode fiber changes with the length of the multimode fiber, and the core-to-core ratio of single-mode fiber and multimode fiber. According to our simulation, we can see that when the length of multimode fiber increases, the number of rings decreases, and the number of modes also decreases. When the core diameter of the step index multimode fiber increases, the number of excited LP0M modes excited increases. The performance of SPR sensor is affected by the resonance angle. The Fresnel equation is used to simulate and calculate the performance of SPR sensor under different fiber grinding angles. As the grinding angle increases, that is, the incident angle decreases, the sensitivity of SPR sensor increases gradually. This is because the evanescent wave vector KEW decreases with the decrease of incident light angle, while the surface plasma wave vector KSP decreases with the increase of wavelength. When the resonance condition is satisfied, KEW is equal to KSP. The wave vector KSP with longer wavelengths can be excited by the light with smaller incidence angle. In the long wavelength range, the change of the refractive index causes greater resonance wavelength shift. Therefore, a smaller incident angle is more conducive to improving the sensor sensitivity. Generally, a larger fiber grinding angle alpha results in a smaller light incident angle theta. Therefore, the sensitivity of SPR sensor increases with the increase of grinding angle. The proposed sensor is fabricated in following steps. First, we connect a section of multimode fiber to single-mode fiber by using fusion splicer. The length of multimode fiber is precisely controlled to generate different types of Bessel-like beams. Thus, the whole cutting process of multimode fiber is carried out under the optical microscope. Second, two symmetrical fiber cones are prepared using the fiber grinding system, and then they are connected together. After coating 50 nanometer gold film on the fiber cones, the sensor is inserted into the capillary tube and embedded in the PDMS chip for refractive index detection. The liquid with different refractive indices are injected into the PDMS microfluidic chip by using micro-injecting pumper. These are the experimental results. The grinding angle is set 12 degrees, and the grinding depth is 62.5 micron. The only variable is the length of multimode optical fiber, and we set it to be 500 micron, 700 micron, 900 micron, and 1500 micron. It can be seen that with the increase of the refractive index of glycerol solution, the resonance wavelength of surface plasma resonance redshifts. It can be concluded that with the decrease of multimode fiber length, the refractive index sensitivity gradually increases. When the length of multimode fiber is 500 micron, it can reach 5378.3 nanometer per refractive index unit. Compared with the same type of fiber optic SPR sensor based on Gaussian beam, the sensitivity has been significantly improved. the sensitivity of the proposed SPR sensor is also affected by the grading angle. Therefore, we set the length of multimode fiber to 500 micron and measured the spectra of the samples with the grading angles alpha equal to 6 degree, 9 degree, 12 degree, and 15 degree. We can see that the larger the grading angle of fiber probe, the higher the refractive index sensitivity. The sensitivity obtained by simulation is similar to the experimental results of all fiber Bessel-like beam SPR sensor, and the sensor performance is slightly better than the simulation results. This is because the all-fiber Bessel-like beam SPR sensor is based on the superposition of multiple similar resonance modes, and the sensing performance is improved. Bessel-like beams have the ability to compress the resonance angle, which increases the excitation efficiency of SPR and leads to a significant increase in the refractive index sensitivity of fiber probes with the same configuration. The table compares the proposed all-fiber optical Bessel-like beam SPR sensor with the previously reported optical fiber SPR sensors. It shows that the proposed SPR sensor has higher sensitivity and lower detection limit. The proposed sensor has the advantages of low cost and simple fabrication, and is suitable for the detection of small dose analytes. The surface plasma wave is a surface wave. Most of its energy is limited to the interface near the waveguide. Therefore, the excitation of SPR based on total internal reflection means that the transmission of light in the waveguide must follow the law of total internal reflection, resulting in the refractive index detection range of the sensor is always lower than the refractive index of the waveguide. In order to improve the refractive index detection range of the SPR-based microfluidic devices, an SPR sensor based on tapered fiber with polymer coating is proposed. The spectra of the proposed SPR sensor with different waveguide refractive indexes are simulated by Fresnel equation. It can be seen that the sensitivity of optical fiber SPR sensor is higher in the high refractive index range. Increasing the refractive index of the waveguide and reducing the difference between the refractive index of the waveguide can improve the refractive index detection range of the sensor and further improve the refractive index sensitivity of the sensor. The probe is prepared with an adiabatic taper to reduce transmission loss. The 532 nanometer laser is coupled to the optical fiber by using an optical coupler, and the polymer coated on the optical fiber taper is formed by photopolymerization reaction with the liquid fiber cladding mode. Compared with the evanescent field, the liquid cladding mode has a higher intensity, which can significantly improve the speed and efficiency of photopolymerization reaction. We are experimentally found that when the fiber taper is thin or when the coating is thick, the polymer material coated on the fiber becomes droplets due to the surface tension. Therefore, it is necessary to select the appropriate taper diameter and film thickness. Here, the tapered fiber diameter is selected 10 micron. Then we test the losses of different samples with the coating thicknesses of 1.8 micron, 2.6 micron, 3.2 micron, and 3.65 micron. The losses at 333 nanometer are 4.6 dB, 5.9 dB, 7.1 dB, and 8.2 dB respectively. The measured refractive index ranges from 1.423 to 1.493 with an interval of 0.01. The resonance dip redshifts with the increase of refractive index. Increasing the polymer coating thickness can increase the refractive index sensing range. However, it is found that the refractive index sensitivity of the fiber optic SPR sensor with thicker coating shows lower sensitivity because the transmission loss of light in the polymer increases and leads to the decrease of coupling degree between the light mode transmitted in the polymer and the surface plasma mode. According to the spectra, we can see that the depth of the resonance dip gradually becomes flat, which indicates SPR phenomenon weakens, and the four-ways of the hot peak of the spectrum increases. Thus, the quality factor decreases. We set the coating thickness to 1.8 micron and test the sensitivity when refractive index is in the range of 1.333 to 1.403. In the low refractive index range, the resonance wavelength increases linearly, and the sensitivity is 1332.9 nanometer per refractive index unit. In the range of high refractive index, the sensitivity is 6422.9 nanometer per refractive index unit, which is about 5 times the low refractive index sensitivity. Because the refractive index of the sample to be measured is closer to the waveguide refractive index, and the refractive index sensitivity of the SPR is higher when the measured refractive index is closer to the phase matching point. As a kind of polymer material, the optical properties of photopolymer also responds to temperature. Therefore, we test the temperature response of the sensor by changing temperature in the range of 20 Celsius to 50 Celsius, and the interval is 5 Celsius degree. With the increase of temperature, the resonance wavelength of SPR shifts to the longer wavelength because the polymer material has a negative thermal optical coefficient. With the increase of temperature, the refractive index of the polymer decreases. When the refractive index of the waveguide decreases, the resonance wavelength of SPR redshifts under the same background refractive index, and the temperature sensitivity is about 1.43 nanometer per Celsius degree. In order to improve the integration of microfluidic optic devices and reduce their volumes, a SPR sensor based on suspended core fiber is proposed. The optical light waveguide is introduced into the capillary optical fiber to construct the sensing area. The air hole in the center of the optical fiber can be used to enhance the fluidity of the liquid. The fiber core can be used to guide light and stimulate SPR. The finite element method is used to establish the simulation model. The dielectric constant and output loss of gold are shown in the formula. The figure shows the mode field distribution, dispersion relation, and mode field loss of the transmitted mode. With the increase of transmission wavelengths, the core mode energy continuously transfers to the gold film. Thus, the energy in the core decreases gradually, and the energy in the gold film increases. When the phase matching is satisfied, which means that the real part of the effective refractive index of the two isolated modes is similar, strong coupling between modes starts to occur until the core mode energy at this wavelength reaches the minimum, and surface plasma resonance occurs. The position of the resonance wavelength is the intersection of the two dispersion curves, core mode dispersion curve and the surface plasma mode dispersion curve, and the maximum loss is 58.6 dB per centimeter. These are the spectra simulated under different gold film thickness. With the increase of gold film thickness, the refractive index sensitivity of SPR sensor increases, and the quality factor of the sensor increases and then decreases. The probe structure is shown in the figure. The SPR sensor prepared with suspended core fiber ensures the liquid flowability. It has the advantages of large aperture and miniaturization and can be used for the detection of liquid samples in small doses. Carbon dioxide laser is used to etch the fiber to obtain a side hole. The length of the hole is about 8 mm. Gold film is deposited on the bare fiber core surface with an ion sputtering instrument. The optical fiber is connected with a polarization-maintaining fiber fusion splicer. Due to the large diameter of suspended core optical fiber, one splits it to the standard optical fiber. A large gap will be reserved at the splitting point, which provides enough space for a liquid sample to flow through the sensing area. Therefore, no additional holes are needed for the optical fiber, which simplifies the fabrication process of the proposed sensor. This is the sensing system. We can see that the refractive index detection is integrated into the fiber. We don't need additional microfluidic chips. In this way, the structure becomes more integrated and compact. We experimentally studied the effects of gold film thicknesses on SPR sensing characteristics by measuring different samples with the gold film thicknesses of 30 nm, 40 nm, 50 nm, 60 nm, and 70 nm respectively. With the increase of gold film thickness, the resonant dip tends to be flat. Because the evanescent field intensity decreases exponentially along the ratio direction, which leads to the weakening of the coupling strength between the core mode and the plasma mode. The relationship between the resonance wavelength and the tested refractive index is shown here. With the increase of gold film thickness, the refractive index sensitivity of SPR gradually increases. Considering sensitivity and quality factor comprehensively, the optimal coating thickness range is 40 to 60 nm, and the corresponding sensitivity is 1,880 nm per refractive index unit to 1,930 nm per refractive index unit. In conclusion, we propose different configurations of fiber optic SPR microfluidic sensors to improve the performance of SPR sensor, including improving the sensitivity, realizing large dynamic refractive index sensing range, and miniaturizing the sensor structure. An all-fiber Bessel-like beam generated by beam shaping technology is used to excite SPR, and the sensitivity of the sensor is significantly improved by compressing the resonance angle. We also use a high refractive index polymer coating as a waveguide to excite SPR. A higher refractive index range can be detected. Theoretically, when the refractive index around the probe is equal to the polymer refractive index, the sensitivity can reach infinity. Finally, the SPR microfluidic sensor made of suspended core optical fiber integrates the detection of small dose of liquid into a single optical fiber, which further reduces the size of the device. To get more details and have a nice communication, please feel free to contact us. That's all. Thank you.